Welcome to Atomic Universe. I'm Dan Bergstrom, materials scientist. The first two episodes of this series have shown how we've learned the world is made of atoms and how the configuration of electrons determine most of the properties of everyday matter, with the notable exceptions of mass and radioactivity. Today, to finish our description of the atom, let's turn our attention to that weighty topic of the atomic nucleus and discuss the protons and neutrons inside. As we touched on last time, the existence of a small massive nucleus at the center of the atom was first proposed by Ernest Rutherford to explain the data that Hans Geiger and Ernest Marsden had collected on alpha particles scattering off of atoms within a gold foil. The alpha particles, which are essentially helium atoms stripped of their electrons, mostly went straight through the gold foil. But a small fraction then smashed off something very small in the heart of the atom, which was hard enough to send the particles bouncing off in all directions. By smashing helium atoms into gold atoms, the inner structure of the atom was revealed, the first ever atom-smashing experiment. When Rutherford published his nuclear model of the atom in 1911, he also included an estimate of the size of the nucleus. Using Coulomb's law, Rutherford estimated that a lucky alpha particle that hit the bullseye could get as close as 3/10,000ths of an angstrom to the atomic center. At that point, the electrical repulsion of the positively charged nucleus would stop it in its tracks and send it backscattering. Rutherford calculated that to be an upper limit on the size of the gold nucleus, which we now know to be about 5 times smaller, because he knew the minimum size he could resolve was limited by the kinetic energy of the alpha particles. Rutherford went on to calculate the distribution of the scattering angles of alpha particles as a function of distance from the bullseye and how that distribution changed for different nuclear charges. By comparing the measured alpha particle backscattering intensities to his calculation, he concluded that the central nuclear charge in various elements seemed to increase linearly with their atomic weight. Soon after reading Rutherford's paper, Dutch mathematician Antonius van den Broek reasoned that if each element has a different nuclear charge, that perhaps to each possible charge per atom belongs a possible element. He even used this theory to publish a revised periodic table in 1913. He assumed a 1:2 ratio for charge to atomic weight based on extrapolation from the lighter elements, but we now know this overestimates the atomic charge by about 20%. As a result, he incorrectly predicted a whopping 24 yet-to-be-discovered elements with his table, when in fact there turned out to be only 3. Meanwhile, Englishman Henry Moseley, working under Rutherford, was developing a way to collect high-energy atomic spectra by analyzing X-ray emission wavelengths. Instead of using a glass prism to separate the light wavelengths as would be used in a normal spectrometer, he diffracted the X-rays off a crystal analyzer and used the recently discovered Bragg's law to calculate the X-ray wavelengths from the diffraction angles. The result he found, known as Moseley's law, was that the frequencies of various spectral lines for different materials scaled as the square of nuclear charge. This was the same dependence predicted by the quantum model of the atom published by Niels Bohr in 1913. With Bohr's formula, Moseley could for the first time in 1914 list the elements in order by their atomic number, a term coined by Rutherford. Moseley also correctly predicted exactly 3 undiscovered elements among the first 80 atomic numbers, and these were in fact all discovered over the next several decades. Based on these results, Rutherford began a reconsideration of Prout's hypothesis. A century earlier, following the first tabulation of atomic weights published by John Dalton, British chemist William Prout theorized that since the reported atomic weights for all the elements were integral multiples of hydrogen, that all atoms were likely built up from hydrogen-like particles he called protiles. As it became clear over the ensuing decades that many atomic weights were not integral multiples of hydrogen's weight, this model was discarded by the scientific community. As it was Rutherford himself who had shown that alpha radiation was really the ejection of helium nuclei from the atom back when he was working in J.J. Thomson's Cavendish lab in Cambridge, Rutherford took seriously the idea that there could be hydrogen nuclei inside the atoms that collectively gave the nucleus its charge. But without any experimental evidence, it was still just a theory. In 1914, World War I broke out, slowing the pace of scientific discovery. Rutherford lent his expertise to the British Navy, trying to detect U-boats with sonar, but he did still find time for some atom smashing, continuing the experiments of Geiger and Marsden, who were both called to military service, but on opposite sides of the war. Before the war, Marsden had detected some anomalously high-energy particles in an experiment where alpha particles were scattered off of air molecules, but he had been unable to determine the source in part due to background radiation from the glass tube he was using. After the war, when Marsden returned to see Rutherford at Manchester, he was hurried into the lab, where Rutherford demonstrated the results of his recent experiments. Rutherford had replaced Marsden's glass work with a brass chamber, as shown here. Inside the box was an alpha particle emitter, a disk of radium, mounted on a sliding fence facing a zinc sulfide scintillation screen at the far end. Although Rutherford could not see the invisible beams of radiation until they hit the screen, I'm showing them to you in the simulation so you can see the action. At close range, the alpha particles from the radium would light up the scintillation screen as in the gold foil experiment, but Rutherford knew the alpha particles only had a range of about 7 centimeters in air, so by placing the source beyond that point, he could concentrate on secondary effects of alpha collisions with gas atoms. Tubes on the top of the box allowed different gases to be introduced for study. Unlike the heavy gold atoms, alpha particles colliding with light gas atoms could kick them forward with great speed, and Rutherford had trained his eye to recognize the different sized scintillations of alpha particles, forward scattered hydrogen ions, and larger gas ions like oxygen. And he had run several experiments to determine the range of these particles. In the case of air, forward scattered nitrogen and oxygen ions had a range of about 9 centimeters, but Rutherford also saw scintillations looking like hydrogen ions, which had much longer range, similar to the particles that Martson had seen before the war. In the experiment shown Martson, Rutherford had added some aluminum foil of sufficient thickness to block everything except this hydrogen-like radiation from reaching the particle detection screen. Next, Rutherford loaded up a series of gases representing the components of air: oxygen, carbon dioxide, and water vapor, shooting alpha particles at all of them in turn while the scintillation screen showed no evidence of hydrogen activity. Finally, when he filled the tube with pure nitrogen, the screen lit up like a war zone of what looked like hydrogen ions. The alpha particles were clearly reacting with the nitrogen in an unusual way to create this never-before-seen form of radiation. Rutherford's suspicion was that he was the first to split the atom and chip off a protyle from the nucleus. Knowing the immense energy of such a nuclear reaction, theoretically, he joked during the experiment, we might go up through the roof. In 1918, J.J. Thomson stepped down as head of the Cavendish lab, and Rutherford moved from Manchester to Cambridge to take his place as Cavendish Professor of Physics. Rutherford continued his nuclear investigations with his new team. In subsequent experiments, Rutherford and his new group proved his suspected hydrogen ions did indeed have 1 unit of positive charge, a mass equal to hydrogen, and so much energy that they must have been liberated from within the nucleus. It was also found that the same hydrogen ions could be liberated from all kinds of light elements, and when they were ejected from the nucleus in all directions. Just as J.J. Thomson had discovered electrons by extracting them from an atom and weighing them, Rutherford had discovered a new subatomic particle to which he gave the name proton in honor of Prout's protiles. To this point, Rutherford had assumed that his original experiment had shipped protons off of nitrogen atoms to form carbon, but he couldn't be sure, and in fact this assumption was incorrect. His team continued to work to prove this really was a nuclear reaction and to pin down exactly what type of transmutation was occurring. One of those team members was Charles Wilson, a meteorologist from Scotland who had been studying cloud formation at Cavendish when J.J. Thomson recommended looking at the effect of irradiation. Wilson had designed an experimental chamber which expanded humid air to create supersaturated water vapor, and he found that any kind of charged particles entering the chamber would precipitate a vapor trail of water droplets in the particle's path. Here is a modern cloud chamber video showing radiation from a piece of radium, with thick cloud tracks from alpha particles and thin ones from beta radiation. Rutherford realized that a cloud chamber picture of his nuclear reaction would be a literal smoking gun that would make clear where the protons were coming from, but Wilson's early cloud chambers were not well suited for the rapid data collection necessary to catch this rare event. British physicist Patrick Blackett joined Rutherford's team in 1921, and Rutherford put him to work on improving Wilson's cloud chamber. By adding a pulsing mechanism to quickly reset the chamber with pressure cycling, Blackett was able to greatly increase the rate of data collection. Repeating Rutherford's alpha scattering experiment with a nitrogen gas background, Blackett collected over 20,000 pictures from a pair of orthogonally mounted cameras. With each picture capturing an average of 18 alpha particle tracks, that was over 400,000 events to analyze. In 1925, he published a handful of instances where he found an alpha track ended with the creation of 2 tracks resembling those of oxygen and hydrogen ions. Assuming conservation of momentum, careful analysis of the tracks confirmed that a nuclear reaction had indeed taken place. An alpha particle had fused with a nitrogen-14 atom, increasing its atomic number by 1 and mass by 3 to become oxygen-17 and releasing a single proton. Thus, Blackett can be said to be the first to achieve the alchemist's dream with photographic proof that atoms of one element could be transmuted into another by creating a nuclear reaction. At the same time as the development of the cloud chamber to be able to better see atoms, another device was being perfected at the Cavendish lab to be able to precisely weigh them. Back in 1910, Francis Aston had joined J.J. Thomson at the Cavendish lab and assisted him to measure mass-charge ratios for various ionized gases. Aston built a device that was able to photograph the parabolic tracks traced by ions steered by perpendicular electric and magnetic fields and calculated the mass-charge ratios of these ions based on the path they took. In 1912, Thomson published their surprising discovery of what Aston called meta-neon, with a mass about 10% heavier than neon's accepted atomic weight of 20.2 mass units. The next year, chemist Frederick Soddy at the University of Glasgow published a study of radiochemistry, in which he coined the term isotope to describe atoms with the same atomic number but different mass that he observed as a result of natural radioactive decay. Over the next 2 decades, Aston continued to refine the technique of what became known as mass spectroscopy, and by the 1920s he had isolated about 40 additional cases of non-radioactive isotopes, showing that the accepted non-integer atomic masses were really averages of isotopic atoms, which did have weights which were very nearly multiples of the proton's mass. At this point, Rutherford reasonably theorized that atomic nuclei were composed of the same pieces they could emit: hydrogen and helium nuclei and electrons, which Rutherford himself had named protons and alpha and beta radiation respectively. He also imagined that electrons were binding together the other positively charged pieces. While incorrect, this inspired him to believe that proton-electron doublets with zero net charge could exist. If so, these neutral particles would explain the mass of different isotopes and had the potential to be great atom smashers, immune from Coulombic scattering. In 1921, it was American chemist William Harkins who came up with the name neutron for Rutherford's hypothetical particle. This line of thinking led Rutherford's lab to quietly run a series of experiments searching for any evidence that neutral particles or doublets could be knocked out of an atomic nucleus. Englishman James Chadwick spent the 1920s with Rutherford working on this problem, running, as Chadwick would later say, quite a number of silly experiments, adding, "I must say the silliest were done by Rutherford." The difficulty was that the particle detectors they had, like scintillation screens and cloud chambers, were only able to detect charged particles. Geiger counters could detect neutral gamma rays, but only indirectly through gas ionization by the radiation. Then, in 1931, Chadwick learned of results by Marie Curie's daughter and her husband, Irene and Frederic Joliot-Curie. In their experiment, alpha particles bombarded a sample of beryllium, a process thought to produce gamma radiation, and sent that radiation into a piece of paraffin wax. This resulted in high-velocity protons being emitted from the wax. Upon hearing of this result, Chadwick very much doubted that gamma radiation, which consists of massless photons, could knock out a heavy proton from the wax. And having spent so many years himself trying to find evidence of heavy neutral radiation, he was willing to bet that this gamma radiation was really a neutron beam. And so, Chadwick spent the next 10 days running non-stop experiments with very little sleep trying to prove this hypothesis. He confirmed that this radiation was neutral, that it could easily pass through a sheet of lead 2 centimeters thick as only a neutral particle could do, and he used the penetration data to correctly estimate the size of the lead nucleus at about 7 femtometers. This was about 5 times smaller than Rutherford's estimate of the nucleus from the gold foil experiment. He also estimated the mass of this neutral particle by measuring the forward scattering of different types of gas atoms, and he found it to be about the same as a proton, but slightly heavier, as would be expected for a bound proton-electron doublet. Finally, Chadwick showed that this particle emerged from the beryllium nucleus in all directions, as was previously seen with particles emitted from nuclear reactions. Having proven to himself that he had in fact discovered the neutron, Chadwick presented the results of his exhausting research to his colleagues at the Cavendish and declared, "Now I would like to be chloroformed and put to bed for a fortnight." The Curies had generated similar data, but hadn't realized their significance. Frederic Joliot-Curie later wrote of the missed opportunity to discover the neutron thus: "The word neutron had been used by the genius Rutherford. This hypothesis had escaped the attention of most physicists, including ourselves, but it was still present at the Cavendish where Chadwick worked. Old laboratories with long tradition always have hidden riches." And thus it was, after Chadwick's results were published in 1932, that Rutherford and the staff at the Cavendish lab could lay claim to having discovered J.J. Thomson's electron, Rutherford's proton, and now Chadwick's neutron. They had a complete set of subatomic particles that could explain atomic structure and the properties of matter. They understood the origin of atomic masses and could weigh the isotopes in Aston's mass spectrometer, and they could describe nuclear reactions and even photograph them in the cloud chambers of Wilson and Blackett. In time, each of these gentlemen would receive Nobel Prizes for their contributions to nuclear science. And despite all these accomplishments, the Cavendish lab wasn't done yet with what later would be termed its golden year of 1932. John Cockcroft and Ernest Walton were about to take atom smashing to the next level by announcing the first confirmed nuclear reaction achieved with a particle accelerator. But that's a story for next time. For today, I'd like to end by giving you an accurate sense of scale for how small protons and neutrons really are. I'll do this by extending the visualization from my first episode, The Atomic Hypothesis. If you saw that episode, you will recall we threw one penny into a fountain and put its twin under the microscope. While zooming in on the penny down to the atomic level, we zoomed out on the fountain, changing both magnifications at the same rate. At the end of that video, it was shown that the ratio of the size of a copper atom to the size of the original penny was about the same as the ratio of the penny compared to the size of Europe. So now let's keep going and zoom into one of those copper atoms. As we move inside, I will peel back the electron energy shells one at a time. Of course, at this point I've switched from real microscope images to showing atomic models. Since we are prevented from saying exactly where the electrons are in the atom by the Heisenberg uncertainty principle, I'm showing contour plots for the electron wave functions. I'll save a more detailed explanation of quantum electrodynamics for a future video. As we continue to zoom out, past the orbit of the Moon on the left, on the right we are just inside the inner electron shell. But the copper nucleus is still far too small to be seen. Only as the Earth fades into the starry background do we begin to see the small speck of the nucleus emerge. At a zoom factor of about 3 trillion times, I'll pause here to show you that the copper nucleus has been enlarged to about the same size as our original penny, and the penny enlarged by the same factor would be about the same size as Mercury's orbit around the Sun. It takes about another factor of 5 zoom to enlarge a single proton to the size of our penny, which, blown up by the same amount, totally eclipses the Earth's orbit as well as that of Mars. That's it for today. Next time we'll take a peek inside the proton to look at the quarks inside, which are so small we can't be sure they have any size at all. Thanks for watching.